Hi guys, thank you for coming. My name is Mario Fusco. I'm from Italy. I work for Red Hat. In particular, I work on rules, which is the rule engine of Red Hat. Today I'm here to speak about functional programming, a specific topic about functional programming, which is very common in functional programming, but not really in imperative languages like Java. So I'm here to speak about laziness. So what is laziness? Programming, in functional programming mainly, laziness is the technique, the possibilities of evaluating a parameter, a value, a parameter passed to a function or to a method if you are speaking about Java, only when the parameter is really necessary, only if and when the parameter will be really used by the function, okay? This, of course, doesn't happen in Java. What happens in Java is that when you pass an argument to a method, the argument is fully evaluated before being passed, okay? So it's all a matter about strictness versus laziness. Java is a strict language, so everything is done up front. So strictness is about doing things regardless, while laziness is about nothing the things to do and just doing that things, okay? And if you think about it, laziness is also really in our human nature. I have a 6-year-old daughter, and at the end of the day, her room is a big mess. And when I say, Sophia, is everything okay in your room? Did you put all your toys away? Yeah, sure, Dad, I'm done. Everything is okay. Okay, I'm coming to check. Okay, wait. I will put everything at place. Okay, so she's lazy, okay? She's not doing her job until it's needed. That is exactly what laziness is, okay? And as I said, Java is a strict language, but of course there are some minor but very notable exceptions, which are necessary, which are the Boolean operator, the ternary operator, of course the loops, the if-else, and there is one more notable exception, which is the first lazy API introduced in Java, which are the streams. Okay, and if you think about it, these exceptions are really necessary. It's really impossible or very hard to think about an entirely strict language. Otherwise, I don't know, if Java was strict in this statement, if you don't have the shortcut end and the person is null, you will get a null pointer exception on the right part of the end statement, if you think about it. So Java has to be lazy in some specific cases. But you can do much more. There is something more. Let's suppose that I want to simulate, to create a method that simulates the behavior of the ternary operator, okay? So this is my method. It takes a Boolean, and if the Boolean is true, I will return the first value, and otherwise I will return the second. But what is the difference between this method, this thing, and the ternary operator? The problem here is that both the first and the second argument will be eagerly evaluated regardless if they are necessary or not, right? So this is the Java strictness. But in Java 8, it's very easy to turn this thing in a lazy evaluated thing. It's enough to replace the argument with a supplier of that argument, okay? So when you really need that value, you call get on that supplier, and only that argument will be evaluated, not the other. Okay, so in this way, I'm really doing the same thing, having the same behavior of the ternary operator. Okay, and this technique is very common. Sorry, my timer is not started. Should I start it or? Okay, sorry. This technique is very common, and there are a few libraries already using it. Before Java 8, if you used a logging library, let's say log4j, you should often use this if statement. Why you need to use it? Because otherwise the string, this string, will be built regardless of the fact if it is necessary or not. And probably it's a very intensive computation to create that string. And you don't want to create the string if you are not tracing. You don't want to waste time creating the string if it is not necessary. So what you do before Java 8 is putting this if around, okay? This is no longer necessary if you think about it by using the technique that I showed in the former slide, because now you are not passing the string. You are in log4j, you can pass a supplier of the string, so you don't need the if anymore, because log4j will invoke the supplier, will create that string if and only if is in tracing mode, if and only if it is really necessary. Okay, so this is why laziness is helping me in a very simple example. And in reality, laziness is the ultimate performance optimization technique. If you think about it, there is nothing better, nothing faster than not doing anything at all. And this is what laziness is about. And as I said, Java 8 streams are a very specific case because it is the very first lazy API introduced in native Java. So what I'm doing here, what laziness allows me to do? It allows me to, first of all, create a potentially infinite stream. If the stream was eagerly evaluated, it couldn't be infinite, of course. Now here I'm defining a potential infinite stream. I'm creating a pipeline of operation. But when I call map, when I call filter, these operations are not really done. I'm just defining the pipeline. I'm not triggering it. Okay? So the creation of the infinite stream is lazy, and the manipulation of the data inside the stream are lazy. What triggers everything is the terminal statement, is defined first in this case. In this case, I'm asking for a result. I'm going to check Sophia's room if everything is okay, and at that point, all operations are triggered, not before, right? Okay, so a stream is not a data structure per se. It's a lazy specification of the operation that you want to perform on a list, on a collection of data. And there are a few things that you cannot do without laziness. Well, you can in reality, but you can do them in a much more elegant way if you use laziness. For example, let's suppose that I want to filter the first 10 primes. And how can you do this using laziness? It's very simple. The algorithm can be described in natural language. I take the list of positive integers, I filter the primes, and then I return the first 10. Okay? Why I cannot do this in a strictly evaluated way? Because I cannot do point 1, for instance. I cannot say, take the list of positive integers, because take the list of positive integers means eagerly create an infinite data structure that contains all the positive integers. That's impossible, okay? So yes, I can achieve the same result in a strict way, but it will be much more cumbersome. It will require a more algorithmic description. Functional programming and laziness are much more declarative. Okay, so yes, it is doable, but it's not so easy. Okay, and there is another important property that derives from this. As I said, with the stream, you describe a set of steps, okay? And then you trick the operation. And each step is described in a declarative way the intention of what you want to do. So laziness is also an enabler for separation of concern. Let me show you this claim with a very simple example. Okay, what I want to do here in an imperative and digger way. I have a file which is a log, and I want to filter only the statement in the log beginning with error, and I want to take the first 40 of them. That's all, okay? And I'm not writing obfuscating code. I think more or less in imperative style you will write something like this. And by using stream, you could write something like this. And in my opinion, the most important thing to note here is, okay, yes, the stream is more compact, it's more readable, but what is also really important is the separation of concern. Okay, because when you use the stream, you are dealing with traversing all the lines in the file in just one single point. You are declaring the filter condition in just one single point. You are declaring the fact that you want only the first 40 result in one single point. Okay, and you are collecting the result in one single point. Conversely, the imperative version, you see all the responsibility are scattered around your code. So this is the most important thing to note, in my opinion, with this small example. So, okay, cool. Now we know. Let's go back to the prime numbers example, and let's solve it using stream. Streams everywhere, right? So yeah, this is a first attempt, and it works. So I just defined a predicate, a method that given a candidate number will return true or false if the number is prime or not. And then I create my infinite stream of integer. I filter this stream with that predicate, and I limit the result to the first end result. Okay, that's all. And it works. The problem with this is that it's not lazy enough, and being not lazy enough has an efficiency problem here. What's the problem? The problem is that every time in the predicate, I'm recomputing, I'm checking my candidate number against all the list of numbers that come before it. Okay, so if I'm checking 11, I'm dividing it trying to divide it by 2, by 3, and that's okay. But I'm also dividing it by 4, and this is a waste because I already discovered by traversing the former primes that 4 is not a prime. Okay, so I don't want to divide. I want to keep track in some way that 4 is not a prime, and I don't want to divide the next candidate by 4. It's a waste. Okay, and I'm not doing this with this example. So let's change. Let's change this. And try to do something like this, okay? So I have two methods here. one to take the head of the stream, which is the first item of the stream, and another to take the tail of the stream, which is the stream without the first item, okay? And I define, okay, the numbers method define the infinite stream. So what I'm doing here is that I'm creating a stream, and then I'm concatenating this by filtering the number using only the head, okay? And by doing this recursively, I'm keeping track in the recursion of the primes that I already found, and I'm not doing this anymore, okay? I'm not wasting my time checking against non-primitive number, because in the recursion, I'm keeping track of the primitive number, the prime number, sorry. Okay, this doesn't work, of course, in Java. Why it doesn't work? Because there are two main problems. The first problem is that with stream, you cannot call two terminal operation. You cannot call two terminal operation on the same stream. Once you call a terminal operation, the stream is done. And if you try to call a second terminal operation on the stream, you will just get an exception, okay? And the other problem is that since Java is not lazy, this recursion will just create an infinite stack without producing any result, okay? Okay. But where is the problem? The problem is not in the idea. The problem is in the implementation of this idea in Java, okay? For instance, if you try to do this in Scala, it works. I'm just writing in Scala exactly the same idea using, yes, this fancy operator is dash colon colon, okay? the name of the operator is questionable, but what this operator does is a lazy string concatenation, okay? So it's doing concatenation, but in a lazy way, which is exactly the thing I need and I don't have in Java. And in Scala, this works, okay? And it is exactly the implementation of the same idea of the former slide. So let's try to do the same in Java. To do this in Java, I need to create a lazy data structure, okay? So here I'm just defining an head-tail list, meaning that this list is a recursively defined list where the head is the first item and the tail is another head-tail list, okay? Very simple. So, and it has a couple of other methods that tells me if the list is empty, and that allows me to filter the list given a predicate. So this is the definition of my head-tail list. Then I can have a lazy implementation of this head-tail list. Why is it lazy? Because if you look, the tail is not, you don't have a reference to the tail, but in this list you have a reference to a supplier of a tail. So you already learned this trick. To make things lazy in Java, you have to replace the argument with a supplier of that argument, okay? And that's why the list is lazy, because yes, I have the head, but only when I ask for the tail will be computed, okay? And computed the tail, what it means? I'm computing the remaining part of the list, but not the whole list, just the first item of the remaining part of the list, plus a supplier for the remaining tail, in a recursive way, of course, okay? And given this data structure, I can define the filter in this way, which is recursive this time, as you can see, but now it works because everything is lazy, okay? And at this point, I can have my my list, which is generated by these primes, which is applying that filter, and as you see, that filter is applied recursively in a lazy way, and is keeping track of all the primes. Okay, so what I do to extract all the prime from this list, I ask for the head, which is the number 2, the first item, and then I ask for the tail, and for the head of the tail, which is again everything is calculated in a lazy way. So this tail will just have the 3 as a value, and the remaining part will be just the suppliers, not computed yet. And you do the same for 5 and so on and so forth. Okay, so just to make clear what is happening under the hood. Okay, I have this which is a factory method that just creates for me a lazy list with an infinite lazy list that starts from m and as a tail all the number after n, starting a supplier of from n plus 1. Okay, so it's the list of all the number from m to infinite. Okay, so what is happening here? I'm creating this list, which is again 2, which is as 2 as head, and the supplier of the list starting with 3 as tail. Okay, and then I call primes on this, so the supplier is filtered. Okay, and is filtered using the head, which is 2 at this point. Okay, and then I call tail on this, and this happen. Okay, so I'm the primes is this, so this part becomes this, is the list is expanding, so is 3 as head plus the from 4 filtered by 2 and filtered by 3, which is the end of this. You see, with the recursion, I'm carry on the list of primes. Okay, so if I do another step, the next step will be from 6 filtered by 2, filtered by 3, and filtered by 5. Okay, is it clear? With the recursion, I'm carry on the list of prime numbers and the filtering only by them. That's why it is that's what it is happening. Okay, and yeah, again, there are a few ways to traverse this list. One is, of course, the iterative way, but in functional programming, it's not always. It's often preferred the recursive way. In reality, we have since Java 8, we have already a couple of different ways of doing iteration, okay, which are quite different. We are used to this, which is the external iteration, but with stream, we do what it is called internal iteration, okay? So, and there is a very important difference between these two things. And I, again, learned the difference by observing my daughter, okay? When she was younger, at the end of the day, the living room was full of her toys, and she had to put everything away, okay? And when she was younger, I had to use an external iteration. What does it mean? What I had to do is saying, Sophia, what is on the ground? The ball. Okay, take the ball and put it in the box. What else is on the ground? The car. Okay, take the car and put it in the box. What else? The doll. Okay, take the doll, put it in the box. I'm externally iterating Sophia, item by item, to allow her to put her toys away. Okay? And finally, Sophia understood that I don't like a messed up living room at the end of the day. And I can say, okay, Sophia, put all your toys away. Okay, and this is the internal iteration, because at that point there isn't anybody externally iterating, driving Sophia, but it's Sophia that is internally deciding what to do with the toys. And why it is important? Because if I externally driving, iterating the toys, I'm just going through them one by one, okay? With internal iteration, Sophia can maybe decide to take the doll with one end and take the ball with the other end and put them together in the box. So she's doing parallel computation on her own, right? Or she could decide to take the ball first because it's closer to the box and the car after. So she's doing instruction reordering, okay? And she can do this because she's in control. The stream is in control. The API is in control, and it is doing this job for you, okay? You could do the same externally, but it would require a much more big effort, because when you are in control, you have to drive this thing, okay? If you leave the internal iteration in control, you can have for free those optimizations. Okay, so this is the difference between internal and external iteration. But as I said, there is a third technique, especially used in functional programming, which is recursion. So I can define the sum of all the first n number also in a recursively way, as I wrote there, okay? And recursion is another technique which is used quite often, and because it can solve a lot of problems in a clever way. Okay, so let's consider this other problem. I have a string, and I want to create a predicate that tells me if the string is a palindrome or not. Okay, that tells me if I can read if it's possible to read the string from left to right and from right to left exactly in the same way. Okay, so what I'm doing here, I'm creating a recursive algorithm. Okay, the first two statements are intended just to remove the non-letter character. Okay, and then what I do, if the string is empty, I know that it's a palindrome, so I return true. Okay, if the very first and very last character are different, I know that it isn't a palindrome, so I return false. Okay. Otherwise, I remove the very first and the very last character, and I call the algorithm recursively by passing the remaining part of the string. Is that clear? Okay. So very simple. So you see, I create not create another string. I pass the same string, but passing also to index to say don't take care of the very first and the very last character, because I already checked them, they are equal. Okay, so this works with a reasonable string, but what's the problem with this algorithm? What happens if I pass to this algorithm a very long string? I will get a Stack Overflow, of course. Okay? Why? Because I'm piling up this call one on the other until I blow up my stack. Okay? And why this is happening? It is happening because Java is missing another possible optimization that is called the TailCall optimization. Okay? That is not only a thing that is used for recursion, but it's very important for recursion because with recursion you have this effect of recursively call the method again and again and eventually blow up the stack. But in general, if the very last statement of a method is the return of the value returned by another method that you are about to call, you can, if you think about it, you can remove that method from the stack. And this is what, for instance, the Scala compiler does. So you can avoid to push the new method on the stack. You just give it the control. Okay, so removing the caller from the stack, the caller is no longer on the stack. You just pass the control to the new method. You are not adding up on the stack. Okay, and this is called TailCall optimization. And this is particularly important for recursion, as I said. But of course, this works only if you know this is the TailCall optimization. So it works when the last method is the tail of the method. It's the very last of the method. For instance, this method there is not tail recursive. Why it's not tail recursive? Because the very last operation is not calling some mole recursively, but is the addition, is the sum. So this is not tail recursive. But there are techniques to, in many cases, to convert a normal recursion in a tail one, like I'm doing here. Okay, here I'm using an accumulator, so I'm converting the recursion in a tail recursion. And why this is important again? Because I can use TailCall optimization. So this is the algorithm that I wrote before in Java. This is in Scala. And as I said, this just works as it is because I have TailCall optimization, which I don't have. In Java. So what can I do here? I can use a technique that is called a trampoline. What is a trampoline? A trampoline is a pattern such that when I apply a function, when I invoke a function, the return is not the result, but another function. Okay? And then I call the function again and again and again, until I find the very last one, and on the very last one, only on the very last one, when called, I will be returned with the result. Okay? Let's try to implement this in Java. I have this TailCall. Yeah, you learned the trick. Everything has to be a supplier. Okay? So this is a supplier to make it lazy. Okay? And then I have this TailCall, which is which has a few methods. Okay, I have a Boolean that tells me if the TailCall this function is the last step in the chain that I showed in a former slide. And this is not the last. This is supposed to model an intermediate function, so I cannot call result on it because it's the intermediate one. And then when I invoke it, I iterate in a lazy way through the getter. So this is another potentially infinite stream. I iterate in a lazy way the TailCall until I find a one which is complete. And then the result is there, and I return that result. Okay, and I have another static factory method which returns that special TailCall, which is the terminal one. And for the terminal one, finally, this one returns true. So this is the completion of the operation. And finally, I can call result on it because it's the terminal one. It will give me the result. Okay. So how can I use this stuff? I have this the predicate that I showed you before, and I have this main method which tries to exercise it. Okay, so it works. Okay. Problem is, I googled a bit and found this very long thing, which is supposed to have a meaning in English. I didn't read it, but it is a palindrome. And of course, if I try to run this again, I will blow up my stack. I will get a stack overflow, as you said. Okay. So how can I use my tail call optimization. First of all, I cannot return a Boolean. I have to return a tail call of a Boolean, okay? And then when I have to return a value, I just return the tail call. This is the terminal operation of that chain of functions, okay? So I told you I created that done factory method. So this done is returning that terminal call, which is, okay, I'm done, I'm finished, okay? And okay, here I have to do the same thing, of course, okay? And now here I cannot call recursively the is palindrome to avoid blowing up the stack. I have to return a tail call. A tail call is a supplier. I made it on purpose. Why? Because I can just do this, okay, and Java will promote it to a tail call, okay? So everything is fine now. Now is palindrome is returning not a Boolean, but a tail call of a Boolean. I just call invoke on this, and I'm done. Okay, now it's working, and also the last thing is recognized as a palindrome. Okay, so what I'm doing here? Okay, I showed you this. So what I'm doing here? I'm just linearizing the call with this trick, with the trampoline. I'm just linearizing the call. I'm not adding up in the stack. I'm linearizing them, and that's why I'm not blowing up it. And laziness is the thing that allows me to do this. Okay. One last example. I believe I'm not a big fan of dependency injection. Don't get me wrong, dependency injection is great, but I feel that sometimes we abuse of it. Okay. And there are a few drawbacks in using lots of dependency injection. Why? Because, okay, it is eager in nature, but we couldn't care till now. But the main problem is that you no longer control the life cycle of your object. You cannot use the new keyword, and you have this, all your beans belong to us syndrome, okay? You don't control your beans anymore. We control when create and destroy them, okay? And so you have a complicated object life cycle, and it sometimes can lead to broken encapsulation if you abuse of it, because since it's something easy to do, you do this dependency injection everywhere, and you have your business object depending on 10 or 50 different dependencies, which is an anti-pattern, of course. Okay, and the main problem is that everything is fine when everything works, but when something doesn't work, and sometimes it happens, it's one problem is that it's very, very difficult to figure out what's going wrong. And the other problem is that if you think about it, you are converting what should be a compile time problem. You should know at compile time that dependency it's not possible for some reason. But in reality, you will discover it not at compile time, but at runtime. Okay? So you are converting a compile time problem into a runtime one, which is not really good, unless you are not a JavaScript developer. Okay, so let me introduce you this scary thing, the monad. Oh. And this particular kind of monad is the reader monad, okay? So you already know some monad in Java. The optional monad, what is the optional monad? The optional monad is something that every monad is a pattern that put a value in a context, okay? So what the optional monad does, it put a value in the context of something that could be there or could not be there. What the stream monad does? It put what is the computational context of the stream? In that case, the value could be multiple, more than one. Okay. Also, if you look at the signature of the method, also the completable future in Java is a monad. What's the computational context of that of the completable future monad? Is that the computation of that value is asynchronous. Okay, so here we have exactly the same thing. What we are doing here, we are doing something a little different, meaning that the value we are putting in the context of this monad is not a value. Well, it is a value, but it is a function. Okay. And why it is a function? Because we want to have a computational context that allows us to invoke this function, but in a lazy way. Okay. Okay. This is what I was saying before. So let's try to put this at work. I have this account. I have a logger, which normally will be injected from some magic dependency injection framework. And then I have some operation that depends on the logger because I want to log the operation made on the account. Okay. And in my example, the logger is just the consumer of a stream, just to keep things simple. Okay. So what happens if I use the account, that account in this way? Okay, this is a very naive example. Of course, nobody is injecting the logger inside the account because I'm using the new keyword, and I will get a null pointer exception. Okay, so let's try using my reader monad. I have this lift operation that puts inside the context of the monad the object and a function that inject the dependency inside the object. Okay, so let's try this here. Okay, I won't show you this. You trust me that it will produce a null pointer exception. But what I'm doing here, I have this reader, which is in reality a function, a wrapper of a function, but a function in the end. And it's a function that goes from logger to account. Okay, maybe with 2G. Okay. And how I create it? I create it by lifting the account. And what else should I pass to this lift? I need to pass a function that does the injection. Okay. What the function that does the injection is simply account set logger. That's all. Okay. And at this point, I can do my operation. So of course, I have to do this operation in the context of the monad. So as you use map for optional, you use map in this case. So I do this, for instance. Okay. And sorry, I didn't import this. Okay, and I can do exactly the same thing with other operation, always, of course, in this context. So I do this. Okay. This and this. Okay. And now what I've done, I've defined all my operation, but I'm not triggering them yet because I don't have the logger. I cannot perform the operation without the dependency. So only now that I want to perform the operation, I can say I can call this function because the reader is a function in the end. It's just a wrapper on the function. Okay, and yeah, I can pass a very simple logger, which is the println method reference, and you will see, you'll get the result. Okay, so yeah, this is what I showed you. What's the bottom line? The bottom line is that you can clearly separate, again, through laziness, the business logic, the moment in which you are defining the business logic, to the moment in which you are triggering the business logic. And only when you are triggering the business logic, you need the dependencies, not when you are defining it, okay? So laziness allows you to draw this line, okay? Yeah, I wanted to show also a more complex example with also, with the flat map allow you to inject the logger in more than one bin at the same time. You can use the flat map for this, which is the same concept that you use for the optional or stream, and this is why I'm using the reader monad. And yes, this is basically the takeaway. So Java is a strict language. You can do some tricks or apply some pattern to make it lazy. And laziness is the ultimate form of efficiencies. And with laziness also favor declarative programming, and declarative programming also favors separation of concepts, which are two nice things that probably we want to have in our code. And the last thing is that, yeah, dependency injection is great, but probably for very simple cases, we can use a technique similar to the one I showed. I'm done. Thanks. And